Hello, this is Huiying. In this video, I'm going to demonstrate my current research project. This project is to use deep learning architecture to assist graphene segmentation. Graphene is one kind of quantum materials that can be formed with different layers, and the differences can be told from the colors on the original images. The original images that we used are from the optical microscope. When they input the original images into a modified unit. This is one of the examples of the raw images. The purple part is the graphene flakes, and the gray part is the background. The ground truth mask shows where the graphene is. When I input the output from a unit to a BTNet architecture, which is my main contribution in this project, and the output for the BTNet is 6 values, which represents the maximum RGB values and the minimum RGB values. We then use the values to find the monolayer and the bilayer graphenes. In this video, I'm going to demonstrate how we segment the monolayer graphene from the raw image. On the right-hand side, it's a deep learning architecture. At the input, we have graphene images, and we input it into a model which initialized with hyperparameters. At the output, we have detected RGB values. There are 6 values at the output, the maximum RGB values and the minimum RGB values. We compared it with the ground truth RGB values in the loss function and use the optimizer to optimize the model. Now I want to move on to talk about the code. For a deep learning model, all the images were loaded in batches. Here we define the function ImageGeneratorRGB. The image generator is to create input datasets and the ground truth datasets in batches. For each batch, there are 32 images. All the input images were created with random choices in a batch. Here we created 2 lists, batch X and batch Y, to store the input images and the ground truth maximum and minimum RGB values. For each image in a batch, the raw images were loaded from COCO dataset and resized it to 256 times 256 pixel size of images. And then we input the raw images in UNet model and get the detect mask. We then multiply the detect mask by raw images. So right now we have the masked raw images, which means that only the graphene part was left and the background was blocked. We also loaded the ground truth masks from the COCO datasets and resized it to 256 times 256. And then we segment the ground truth monolayer on the raw images by multiplying the mono mask by masked raw images. Here we created an array RGB_UL to store the maximum RGB values and the minimum RGB values for the monolayer graphene. Here the tricky part is to make sure when we are getting the minimum values for the RGB values, we make sure the background value is 1 instead of 0. In this case, when we are getting the minimum values, we make sure that we are not getting the values from the background. We then append the masked raw images to batch X and the RGB_UL to batch Y. For the input images, we make sure to augment the raw images because we want to increase the input datasets. Here we yield batch X and batch Y. The yield here is to produce a sequence of the batch images. After defining the function, we then can build the training and the testing generators separately. After building the training and the testing generators, we can use them for the BTNet architecture. For the model, we need to define hyperparameters for the training, and the epochs here we set was 300. And this is the architecture for the model. BTNet architecture is a modification version of the classifier. There are 6 classes for this model, and each class stands for a maximum or a minimum RGB value. There are 4 convolutional layers in our model and 2 max pooling layers. The max pooling layers here are used to extract the more important features from the input. The differences between the classifier and our BTNet is the last layer. Here we change the softmax from a classifier to a sigmoid function. The softmax will make sure the sum up of the output to be 1, but here we only want to measure for each output the range of the output to be 0 and 1. So we modified the last layer and changed the softmax function and replace it with a sigmoid function. And there are 6 outputs from our model, which represents the maximum and the minimum RGB values. We then can compile our model. We use the add-in as the optimizer here. And then we compile the model using the loss function mean absolute error. We then fit the model with training generators and testing generators and the hyperparameters. Finally, we plot the loss functions during the training and the validation process. The loss function here was to make sure that the loss converges in the training and the validation process. And here it sums up my current research and the main contribution I've made.